In this video, we'll discuss different types of functions. But first, let's review the definition of binary relations. So, binary relation on A cross B is a subset of the Cartesian product of A and B. So, let's look at this example again. We have two sets A and B. A is a set of students, Zoe, Tommy, Jane, and Noah, and B is a set of classes, CS 104, CS 170, and Math 125. We can see that is taking is a subset of the Cartesian product of A and B, so that's the students cross courses, and it is a binary relation, which is the ordered pairs A and B, such that student A is taking course B. Now we've listed all of the ordered pairs shown in the diagram, which indicate what courses students are taking, such as Zoe taking CS 104 and Tommy taking CS 170. We can also observe in this case that is taking binary relation is a proper subset. And what I mean by that is that there are some ordered pairs in the Cartesian product of A cross B, which is students cross courses, which are not included in the is taking binary relation. So the Cartesian product in this example would be the combination of ordered pairs of students taking every possible class. So the Cartesian product of A and B would be of size 12. There'd be 12 pairs. So we'd have to have Zoe taking 104, Zoe taking 170, Zoe taking Math 125. So we'd have to have an ordered pair including each student for each class. So that's why the size of the Cartesian product would be 12, but you'll notice that is taking binary relation does not have that many ordered pairs in it. Therefore, we can find an ordered pair that's not in the binary relation. So we note that Tommy's taking 170, but Tommy is not taking Math 125. So the ordered pair Tommy, Math 125, is not in the is taking binary relation. Now, let's consider the inverse of a binary relation. A binary relation is on the Cartesian product of A cross B, and its inverse, the inverse of the binary relation R, is a subset of the Cartesian product of B cross A. So the inverse of a binary relation is the set of all ordered pairs y, x, such that the ordered pair xy is in the binary relation. So in plain terms, it's the set of all ordered pairs where the ordered pair in the original relation, xy, is flipped. Now let's look at a concrete example. So once again, we have our set of students, Zoe, Tommy, Jane, and Noah, and we have our set of courses, 104, 170, and 125. Now here we have a smaller relation where our relation R is just two ordered pairs. So we have Zoe taking 104, so Zoe 104, and Tommy taking 170, so Tommy 170. And the inverse of this binary relation R is just flipping the courses and the students. It is a subset of the Cartesian product of the courses cross student. So here we have CS 104, Zoe, and CS 170, Tommy, as the second ordered pair in the inverse of the binary relation R. Now, let's discuss functions again. So a function going from A to B has A as its domain and B as its codomain. Now, functions are types of binary relation, and we'll review that again in a moment. But sometimes you may see functions written in other ways, and we just want to specify that they all mean the same thing. So in a function, we take an element in A and we associate it with an element of B. So how can this be done? Sometimes you'll see an arrow, A to B, which means A is mapping to B, or F of A equals B. That may be how you've seen it more commonly in other classes. Or you can even specify a function as an ordered pair because it is a type of binary relation. So for example, we have F of Tommy equals CS 170, and this can also be specified as the ordered pair Tommy CS170. So it's mapping Tommy to CS170, as we had seen before in the is taking relation. And the important aspect of a function is that every element in the domain must have one arrow coming out of it, which means that it has to map to something in the codomain. This is important because in the binary relation for a function, each element in the domain must be included in one ordered pair and exactly one ordered pair in the functions that we'll be discussing. Now, let's discuss the image of a function. If we have a function f going from the domain A to the codomain B, the image of an element of the domain A is going to be the value of A under the function. And we refer to this often as f of A, and f of A is going to be an element of B, the codomain. Now, if we have a subset of the domain S, its image, f of S, is going to be the set of images of all of its points. So more precisely, the image of a set S that is a subset of the domain A is going to be the set of all points f of x such that x is in the set S, and the image of this set S will be a subset of the codomain B. Now let's consider a concrete example. So we have this function which is mapping the students to courses again, and we want to look at a subset of the students. So in this case, our set S is the set Zoe and Noah, and we want to look at what the image is. So both Zoe and Noah are only mapping to 104s. So the image of the set Zoe Noah is the set containing CS104, and that is a subset of the codomain. Now, we had mentioned sequences before, but now we can talk of sequences as functions. So we can think of sequences as functions going from the non-negative integers or the positive integers to some set that we want to be the codomain. And we've seen sequences before, and often when we see sequences, a term of the sequence is denoted by a single variable, in this case a, with a subscript n, which will have a non-negative integer, often n, and that denotes the image of the integer n. So in this diagram, we started drawing a sequence from the positive integers to the positive integers, and we are taking a positive integer, in this case starting with 1, and we're squaring it. So in particular, we have 1 is going to be the first integer in our sequence, so we could label that A1, and then we'll take 2 and square it. So our second integer in our sequence is going to be 4, and our third will be 9, and so forth. So we can also think of this as saying that f of 1 equals 1, f of 2 equals 4, f of 3 equals 9. And you'll notice that essentially what we're doing is, this is how we often give sequences. This is what this notation means when we give a single variable and give it a subscript with a non-negative integer. It's basically denoting this function, so it's a little bit redundant what I had written to say f of 1 equals the term in the sequence. So, but we can actually think of sequences as functions from the non-negative or say the positive integers to some other set that we want to be our codomain.